Hello everyone, welcome to Aspen Plus tutorial video. So yeah, I'm back. And today I'm going to talk about extractive distillation method to separate an azeotropic mixture of acetone and THF. THF here is basically a short form for tetrahydrofuran. It is a solvent basically. As opposed to focusing on the setup of the flow sheet, which consists of the first column to separate a lighter component and then the second column to separate the solvent, I would like to put more emphasis on an approach on selecting a suitable solvent or entrainer for your extractive distillation setup. So in this case, we're gonna go over or we're gonna explore how the relative volatility of the mixture consisting of the acetone, THF, as well as the entrainer changes using a pseudo-binary vapor-liquid equilibrium, which are available in Aspen. So yeah, let's begin. Before we delve deeper into the discussion of azeotropic distillation, I would like to go over our design problem. So basically, we have a binary mixture, a two-component mixture consisting of acetone and THF, 62 by 38% by mass. And then the stream flows at a flow rate of 0.3 cubic meter per hour at pressure of 1 atm and then 30 degrees Celsius. So of course, these components or this mixture need to be separated to obtain a high purity THF as well as acetone, ideally greater than 99.99 weight%. Well, unfortunately, this mixture is an azeotrope, and as we all know, just to give a basic recap of what azeotrope means, azeotrope is a liquid mixture that has a constant boiling point, and the vapor phase and liquid phase has a similar composition. So basically, this at a certain temperature, if we're talking about the vapor phase composition and liquid phase composition, it will be located at the XY line of your pseudo-binary VLE diagram. So when this happens, further enrichment is not going to be obtained. So of course we need to do something about it. To alter or to modify this azeotrope, or to eliminate this azeotrope, a solvent or entrainer is added. In this case, we're gonna use a solvent to filter ratio of 3:1 to break the azeotrope. Just to go over our task, so the first thing that we want to do is we will try to find the azeotrope of acetone and THF. That's the first task. The second task is to find the best entrainer or solvent for our extractive distillation system. And lastly, we're gonna create our setup, flowsheet setup to to simulate our process and hope to get a high purity product. Just FYI, acetone boiling point is 56 degrees Celsius, and then THF boiling point is 66 degrees Celsius. So, well, when talking about boiling point difference, this can be separated using a simple distillation, but unfortunately they form azeotrope, so we have to break the azeotrope to obtain a high purity mixed component. Oh yeah, before I forgot, I would like to mention that this design problem was taken or was extracted from this research article published in the Chemical Engineering Research and Design by Yuan et al., published in 2015. I encourage you to go over these references if you want to know details on their methodology or their approach in doing the simulations. In terms of the information required to conduct the simulation, these are all of it. We're going to use Uniquac model, and then here EDC here is your extractive distillation column. These are the details where we have stages, feed stage, solvent stage, distillate rate, refill ratio, condenser, blah blah blah. And then as regen here is basically solvent regeneration. These are the details. And then we have our cooler here operating at 30 degrees Celsius and then 1 atmosphere pressure. And of course, this return stream here will be recycle back to the EDC, but I'm not going to go over the recycling processes. All right, before we go into our simulation, I think it would be a good idea for us to get background information on the azeotropic distillation, or in this case, extractive distillation. You know, just by a simple Google search, you can get the information about azeotropic distillation. It's basically a process or technique that used to separate two component mixtures that form azeotrope by adding a solvent that form or creates a lower boiling point azeotrope that is heterogeneous, meaning that they will form two immiscible liquid phases. So in terms of setup, it is quite straightforward. So we have two columns. The first one here is called EDC, where we have a solvent along with feed, enters at the different stages in the column. And in this case, we will separate a lighter component. In this case, we shown in the light D here. Light D here is light distillate. In our case, we're gonna obtain a high purity acetone. And then, of course, in the heavy S stream here, meaning that we have a heavy distillate. Plus solvent will enter the solvent regeneration unit, the second column here, where we're going to separate heavy distillate, and in this case THF, while our solvent, whatever solvent that you choose, will be the stream at the bottom of your column, and then it will be cooled down, and finally recycle back to the first column, which is your EDC. Okay, when talking about solvent selection, ideally the solvent should be cheap, inexpensive, stable thermally, have low toxicity, high boiling point, and simple recoverability. So these are the characteristics of a good solvent or entrainer for your azeotropic distillation. And of course, when you select the solvent must also increase the relative volatility of the mixture, and when you add them, it will not form another azeotrope with the other components. So that's the most important part. Okay, we're talking about the paper that I got this design problem from. This paper, as I said, they focus on the selection of the solvent. So, well, of course, in addition to this characteristic, of your solvent, they decide on what solvent to choose based on the polarity principle. Polarity that are close to heavy components will induce interaction with heavy components and solvent, thereby will modify the relative volatility of the mixture. And of course, since polarity is just a separation of charges when we're talking about the molecules, and one way for us to quantify this, what is called polarity of a solvent is by measuring the dielectric constant of the solvent itself. So high polarity solvent will have a high dielectric constant. And ideally, in this case, it should be in between acetone and THF. All right, I think that's it. Let's go to our simulation. All right, these are my Aspen Plus software. The first thing that I will do is just add the components. So the first component is acetone. The second one here is THF. Okay, the third one here is okay. There are 4 solvents that I will select, or the author of the paper select, which are butyl ether, that's the component. As I said, how they select these butyl ethers and then all the other 3 components is based on the dielectric constant of the chemical itself, and it should be in between the THF as well as acetone. Okay, the second component is xylene. They didn't really mention which xylene, so I'm going to use a paraxylene. Let's see. Xylene. Yeah, I'm going to use a paraxylene, so add the compound, add. And then the third component is a trimethyl. benzene. Yeah, it's going to take a while for it to search. Oh, no match. All right, did I write down incorrect? Try methyl benzene. Okay, how about all right, so what I'm going to do is just type benzene and then search one by one. All right, it should be 135. 135. Here, 135 trimethyl benzene. Extract that compound, add. And then the last one is 1,4-diethyl benzene, which is this one, add certain compound, add, and then close. All right, I have a list all of the components. I'm gonna rename for easy identification. So butyl ether, rename. This one is just xylene, I guess. Try maybe benzene, for example. Dibenzene, I guess. BNZ should be okay. Rename. All right, should be good. And then hit next. I'm gonna use Uniquac following the papers. Uniquac. Enter. Hit next. I'm just gonna click this guy. Hit next. Okay. Yeah, run property simulation. All right. From our task, the first task is for us to find our azeotrope. So again, it's quite simple. I probably have shown this one before. So we're going to go to the binary analysis. And then I'm going to choose TXY diagram. So I'm going to use, in this case, mass fraction at 1 atm and then run analysis. As you can see here, this is the TXY diagram for acetone THF mixture at 1 atm. All right, I'm not going to talk about this here because I already transferred the data into my Excel. So what I did was I go to this input and then I go to result. So I will collect this temperature. That's the first one. And then I will collect this, the second one. And then I will also collect, I think, this guy, if I'm not mistaken. Collect all of these 3 columns into Excel or whatever plotting software that you have, and then you will create the TXY diagram. All right, let's go back to our slide to discuss our TXY diagram. Actually, I also in addition to TXY diagram, I also create another diagram which I call pseudo-binary VLE diagram. Basically, I took the same thing, same data, and then I just transformed them into a different plot, which I call a pseudo-binary VLE. So as you can see here, this is the acetone in y-axis. These are y, by the way, as a type is incorrect here. These are y, and these are x. Acetone composition in y in vapor phase. This one should be x in liquid phase. These are xy line. Basically, anything that in this line is basically has a equal composition, meaning that they form azeotrope. This is what people call as a pseudo-binary VLE diagram. Normally, the common that you always see is called, what is it, a TXY diagram, where you have a temperature in this y-axis, and here you have the composition of your component, in this case acetone in mass composition or mole composition, and then you will have a two plot, which is the one belongs to the vapor phase, the other one belongs to the liquid phase. But in this case, as opposed of having plotting the temperature versus composition of liquid and vapor, I put in pseudo-binary VLE, they put acetone composition in vapor phase, these are Y, in the Y-axis, and then acetone composition in liquid phase in the X-axis, and then plot them here. And of course, these are not that clear. So what I did was this yellow region here, highlighted. This region highlighted in yellow is seen on the second graph. These are the zoom in version of it, where you can see in this at this point around 0.86 roughly weight percent of acetone in liquid phase. These are X. Just want to remind you, they form the composition are the same composition for what is called for liquid phase and vapor phase, and this actually occurs at 55 degrees Celsius. I checked with other references and they are similar as well. All right, so the first task complete. So we have identified that this THF and acetone do form azeotrope, and I was able to show them using the pseudo-binary VLE diagram, and the composition is 86 weight percent occurring at 55 degrees Celsius. All right, let's return back to our Aspen Plus. So what to do next? All right, the second task for us is to find the best solvent that can be used for our extractive distillation. If you remember, we have identified, or the paper have identified 4 potential solvent, but we will try to select which one is the best solvent. So what I'm going to do is I'm going to go back to my input of the binary analysis here. So go to binary analysis. So in here, I will activate pseudo-binary system. So I would choose, let's say for example, I would choose diethylbenzene as my solvent, and then the fraction here is 0.75. So is it, no, I'm sorry, 0.73. And then again, I will run my analysis. And as you can see here, in the TXY diagram, we do not have any more, I would say, azeotrope, which is good. Just want to mention that I repeat the same stuff for different solvent, and I maintain the fraction of 0.73. All right. In the paper, they just simply mention that solvent to what is it called? Solvent to feed ratio is 3:1. So I did the math. It is around 0.73 fraction by mass. All right. So what I did was I go to the result. Okay, to create a pseudo-binary binary VLE. Again, what I did was I choose a mass fraction of acetone here, but in this case, I did not select this guy. Actually, I initially used this guy, but it doesn't, the results are not the same with the published work. But I found out that the result will be the same if I use this one, vapor rate mass transfer, I guess. I don't know why, but I don't know, it is what it is, I guess. So basically, I took this, and then I took this, and then I create a plot, and then I repeat the same thing for the other solvent, and then I plot them in an Excel or whatever plotting software that you have. So let's go back to PowerPoint and then analyze our result. All right, this is the result. As I said, we investigate 4 types of solvent, and the solvent fraction is maintained at 0.73 by mass. biomass. Yeah, as you can see from the first plot, these are acetone fraction in Y. Here is vapor phase. Here is acetone fraction in a liquid phase. These are the black line here, black continuous line here is your XY line. And then the green one here is our acetone THF mixture. And then the rest are the, the plot or the curve for when we add entrainer or solvent or different types of entrainer. Now, why did I choose a xylene? Oh no, I'm sorry. Why did I choose butyl ether here? As you can see here, when we use a butyl ether, they provide us with the largest volatility increase when compared to other components. So this is so based on this, I decided to choose butyl ether. Not I, but the paper. The author of the paper decided to choose butyl ether. If you want to see how my pseudo-binary VLE looks like compared to their papers, you can just download the papers and then compare side by side. All right, what will happen for the TXY diagram if I add the butyl ether 0.73, it becomes like this, where I have a temperature here on y-axis and acetone. Not X and Y, because these are the XY diagram. Acetone, the blue one is a liquid phase, the maroon one is in a vapor phase. As you can see, there are no azeotrope form. So in this, so based on this result, we have identified our best solvent, which is a butyl ether. So what to do next? Okay, once we have identified our solvent, we're going to create our flow sheet and then try to run our simulation and hope to get a high purity product. All right, let's go back to our Aspen. All right, as you can see here, this is the flow sheet which I have created earlier. As I said, the flow sheet is pretty simple. 2 blocks of red flag for extractive distillation, as well as solvent regeneration, and then I have a cooler here and connect the stream as usual. And as I said, this should be recycled back to the first stream, but I decided not to do that because I don't want to deal with these tear stream issues or whatever, So I just keep it simple. All right, hit next. Here I will specify the temperature of the feed, 30 Celsius, and then 1 atmosphere. Volume flow rate is 0.3 cubic meter per hour. Here I specify mass fraction 0.62 for acetone and then 0.38 for THF. Hit next. These are my solvent, 30 degrees Celsius, 1 atm. So solvent to feed ratio is 3:1, so the volume should be 0.9 cubic meter per hour. And here I have a mass fraction of 1 for butyl ether. Why butyl ether? Because in the task number 2, we have found out that butyl ether gives the largest volatility increase for the mixture. All right, hit next. This is my cooler unit, so specify 30 degrees Celsius. I specify no pressure drop, you know what, maybe 1 atm, because what goes in is 1 atm. And then hit next. These are my EDC. My EDC is operating at reflux ratio of 3. Distillate rate is 2.61. And stages 53. Condenser is a total condenser. And then here I have a feed stream enters at stage 24, and solvent enters at stage number 7. Pressure, okay, these are the pressure, the paper said that the pressure, condenser pressure is 0.9, so I'm just going to follow the paper, 0.9. And I hit next. These are the solvent regeneration units. So the stages here is 17, following the papers. total condenser, and then distillate rate is 1.28, and then reflux ratio is 3.5. Stream, the feed stream enters at, I forgot, but I think it is stage 10. Yep, I think stage 10. I'll check, but I think stage 10, but we'll check the result. Pressure here, the pressure is 0.9 atm, the condenser pressure. So, and then I have completed input all of the necessary information. So hit next, I run the simulation. All right, I have completed my simulation, got result available. Again, you can just go to result summary and then analyze them individually in detail if you want. And again, I decided not to discuss them here, and I have extracted all of the necessary information and then transferred them into my PowerPoint. So yeah, let's go back to my PowerPoint. All right, guys, these are my simulation result that I have extracted from the simulation, tabulated them in a form of table. But before we discuss this table, I would like to mention that the feed stage for the S regen or solvent regeneration unit is 10. So basically the number that I input was correct. All right, let's go and check our result. And as you can see here, I was able to get 99.7% of acetone, having a good recovery. So I got 151 kilogram per hour from 152. Heavy key is 99.5. Was able to get again 92 out of 93 kilogram per hour of THF. And finally, our butyl ether was able to get almost 100%, which is 99.9% of butyl ether. Good recovery as well, which is 684 kilogram per hour. So in summary, we are able to obtain our high purity acetone, or basically we was able to separate acetone from THF, having a mass purity of more than 99.08%, or in this case, I was able to get 99.7, 99.5, and 99.9 weight%. And of course, good recovery as well, because having high purity but low recovery is not great. So make sure to have those two conditions met. All right, that would be all from me. If you like the videos, give it a thumbs up. Consider subscribing to my channel, and I will see you guys again in the next video. All right, bye-bye.